There's a theorem out there that claims it can solve any equation. Seriously, any polynomial equation, no matter how ridiculously complex. Now, for centuries, that was considered completely impossible. So let's dig into why that was and what's changed.
I mean, for hundreds of years, this was the consensus. The greatest minds in math believed that finding a single universal formula for these kinds of equations was a total dead end, just impossible. But then, one mathematician, Professor Morad Sultan Ezouidi, claims to have built it. He says he has a theorem that offers a step-by-step way to find the exact answer for any of them. So, let's break down exactly how he says it works.
Okay, so first things first, let's get a feel for the sheer size of the problem here. I mean, we're talking about a challenge that mathematicians have been wrestling with for centuries. So the equations we're talking about are called polynomials. You probably remember these from algebra class. They're just expressions with variables and coefficients. Now, the key thing here is the degree of the polynomial, which is just its highest exponent. That little number up top tells you how complex the thing is. And as you're about to see, that's exactly where all the trouble begins. And here you can see this massive dividing line in mathematics. You see, for any polynomial that's degree 4 or less, we've got formulas for that. They're reliable, they give you the exact answers, but the second you hit degree 5, everything just changes. It was proven that no single formula using what we call radicals, things like square roots, cube roots, that kind of stuff, could solve every single equation that complex.
And that's the absolute crucial point. It was established by something called the Abel-Ruffini theorem. And this theorem basically put up a giant brick wall in the middle of mathematics. It said, nope, you can't solve these harder equations with the tools you have. And for almost 200 years, that was it. That was the limit.
Right, so how do you solve something that's been proven to be unsolvable? Well, this is where Professor Morad Sultan Ezouidi comes into the picture. He developed a new theorem that's so clever because it doesn't even try to smash through that wall. Instead, it claims to have found a way to just walk right around it. And look, the claims for this thing are huge. We're talking about reconstructing every single root. Exactly. It can automatically tell if some roots are repeated. It supposedly works for all polynomials, even the really messy ones they call degenerate cases. And here's the kicker. It does all of this without using any of those radical solutions we just mentioned. So you're probably asking, how on earth does it work? Well, instead of just attacking the equation directly, the theorem does something really smart. It creates a brand new related polynomial. They call it an associated polynomial. And this new equation is like a secret key. From that key, it pulls out these special clues called recursive invariants. Think of them like fingerprints that never change. And by following these fingerprints one by one, like a detective on a case, the process can uncover every single solution to the original puzzle. Okay, but hold on a second. If a super famous theorem said this was impossible, how can this new one work? Is it just breaking math? The answer is nope, not at all. And the way it gets around the problem is, honestly, kind of brilliant. And here it is. This is the big aha moment. Remember the Abel-Ruffini theorem? It only says you can't solve these equations using radicals, square roots, cube roots, and so on. Well, Ezouidi's theorem just doesn't use them at all. It uses a totally different method based on the structure of the equation itself. So it's not breaking the old rule, it's just playing a completely different game. This table really lays out the difference. You can see how the older methods struggle with things like repeated roots or really complex equations. Ezouidi's theorem claims to handle all that no problem. But the real game changers? Check out the bottom 3 rows. Classical methods are all about radicals. This one doesn't touch them. They don't really use invariants. Here, they're the entire foundation. And those messy degenerate cases where the old ways just fail, this new approach is built to handle them perfectly. Okay, that all sounds great in theory, right? But does it actually work in the real world? Let's put it to the test and see how it handles an absolute monster of an equation. So the theorem was thrown at this beast, a 20th degree polynomial. I mean, look at that thing. Trying to solve this with the old methods is just not going to happen. You might get close with a computer approximation, but you'd never find the exact answers. And that's exactly the kind of impossible challenge this theorem was built for. But what's so cool is how the method turns this chaos into a simple step-by-step process. First, you just grab the coefficients. Then you build that special associated polynomial we mentioned. From there, you calculate those recursive invariants. Remember, the fingerprints of the equation. And those invariants are what let you finally piece together all of the exact perfect roots.
And as the professor himself puts it, this isn't just some fancy computer guessing game. It's a structured, logical process that's designed to give you the precise, mathematically proven roots for equations that, until now, were thought to be unsolvable in this way. So, okay, it can solve one crazy hard equation. But what does this mean for math in general? What's the bigger picture here? Well, if this theorem really holds up, the impact could be absolutely massive.
I mean, think about it. We're talking about a truly universal method that could work for a polynomial of any degree, a really robust tool that can handle even the strangest, most extreme cases. It's a solid, rigorous framework that doesn't throw out the old rules, it just builds on top of them. This could potentially unify a whole bunch of different ideas in polynomial theory under one single, powerful approach.
And that's really the bottom line here. It's a solution that is completely independent of the degree. It doesn't care how big that number is because it operates on a deeper level, on the fundamental structure of the equation itself. It's a powerful new chapter for classical algebra. And all this leaves us with a really fascinating question, doesn't it? For 200 years, this problem was basically solved. Everyone agreed it was impossible. But this new approach didn't prove the old theorem wrong. It just found a new way forward. It really makes you wonder, what other impossible problems out there are just waiting for somebody, somewhere, to come at them from a completely different angle?